Good morning to everyone present here. Today our discussion topic will be on Parity Bit Generator or checker. Now, what is the necessity of using this Parity Bit Generator? Now, normally what happens when we need to communicate a particular information, we require two such boxes. One will be a transmitter. This is what we call a transmitter, and this is receiver. Now what happens when we need to transmit certain information from a transmitter to a receiver through certain transmission line? In that case, what happens when we need to transfer the information, there might be certain amount of information lost due to various different types of noise or disturbances or natural calamity that might affect to my data. Suppose the information which we are sending, like 1101, is the information which has to be received by the receiver. But the information received by the receiver might be like this. So what happens? There will be an interchanging in the bit between these two, and therefore the information which is received by the receiver will be an erroneous one. To avoid such type of erroneous error, or rather such type of error into our system, we need to use Parity Bit Generator and checker. So in order to generate the information, we need Parity Bit Generator, and so that the receiver receives the correct information which is transmitted by a transmitter through a transmitter line, we need a parity bit checker circuit or combinational circuit present before the receiver, such that it checks and then receives the correct information or other correct data from the transmitter, and then it is sent to the receiver to receive the information. Now, binary data, when transmitted and processed, is susceptible to noise that can alter its ones to zeros and zeros to 1. To detect such error, an additional bit called a parity bit is added to the data's bits, and the word containing the data bits and the parity bit is transmitted. At the receiving end, the number of ones in the word received are counted and the error, if any, is detected. This parity check, however, detects only one single error. A parity bit of a 0 or a 1 is attached to a data bit such that total number of ones in the word is even for even parity and odd for odd parity. The parity bit can be attached to the code group either at the beginning or at the end, depending on the system design, which means that depending upon number of 1 present here, suppose if we want to make this number an even parity number, in that case what we see, we are having odd number of ones. To make it even parity, I need to add 1 either before or at the end, depending upon my design, to make it even parity. But if we have a number and if we want to detect odd parity, then already the number which is provided to me is the correct number. So we need to add zeros in the front or in the back, depending upon the design. Now, at the receiving end, if the word received has an even number of ones in the odd parity system or an odd number of ones in the even parity system, it implies that an error has occurred. In order to check or generate the proper parity bit in a given code word, the basic principle is used, that is, modulo sum of an even number of 1 is always a 0 and modulo sum of the odd number of 1 is always a 1. Therefore, in order to check for an error, all the bits in the received word are added. If the modulo sum is 0 or an odd parity system of 1, for an even parity system, an error is detected. So to generate an even parity bit, 4 data bits are added using 3 XOR gate. The sum bit will be the parity bit, which means that if we want to add up those numbers, we need to use the gate which is necessary for the parity will be the XOR gate. Using the XOR gate, we are going to add one after the other to find out whether the checker gives the correct answer or not. And to generate an odd parity bit, the 4 data bits are added using 3 XOR gates and the sum bit is inverted, which means if you have supposing 3-bit parity checker, so you will be adding first suppose A and B. These 2 parity bits will be added using XOR gate. Then the result of this will be added up with next bit. That means, as I said, we have a 3-bit parity checker. Finally, this particular parity bit, that is either even or odd depending upon the one which you are checking. If you are checking for an even parity, next even parity bit will be again added up with the last bit in the form of XOR gate to find out whether the answer is correct or not. That means if I use even parity, the summation of all the XOR should give me 0. If this gives me the answer 0, then it is no error. Or else, if after adding all these bits in the form of using the XOR gate, answer becomes 1, then the system, or rather the checker, is giving me a wrong answer. Same thing which says, as we know that the even parity, if it is inverted, it produces an odd parity. So if I use this inverted parameter here, inverted gate here, then if the output of this inversion gives me 0 for odd parity, then the answer will be error. And if I receive 1 for odd parity, the answer will give me no error. So now how to create this even parity generator combinational circuit? Now for this we have to use 3-bit parity. That means we need to use A, B and C. These are the 3-bit, and since I am using for even, using it for even parity bit generator. So for this it should be P suffix E, even parameter. Now this is 3-bit and I have to check even parity. That means that number of ones present in the bit should be equal to an even number including the parity bit. So now if I write down the numbers for binary 0, 1, 2, 3, 4, 5, 6 and 7. These are the 0 to 7 binary numbers in form of 3-bit. Now look at the first bit. In the first case, what do we see? There are no ones present. That means we don't have to make we do not have to add any 1 here to make it even or odd, because it's already odd here. So we'll get here 0. Next we can see in this bit 001, one particular 1 is here which is odd. To make this particular line even, we need to add 1 at the parity bit to make even number of 1. Same way for this one also, we have only one odd number of 1 here. So to make it even, I put here one more 1. For number 3, we see we have 2 already 1 given here, which is already making it even. So we do not need any more 1 in the parity bit to make it even. So we'll put here 0. Next will be number 4. This has only 1 number here, that is odd number. So to make it even, I'll put here 1. Then for the next line, we see number 5. We have already 2 1 here. So the parity bit will give me 0. Next for this line, we see for 6, both of them are 1 here, which is making even number of 1. So here will be 0. And finally we see these 3 are 1, that is for 7 of decimal 7. So what do we see here? Since there are 3 numbers are all 1, that means odd number of 1 is present. So to make it even, I would have to put 1 at the parity generator bit. So what do we see? After this, we need to create the combinational circuit. For this, we need to use first K-map and then finally the logic gate. So to make a K-map, we need to first draw the K-map cells. As we can see, it's 3 bits, so 2 to the power 3 will give me 8, which means we have to create 8 cells for K-map. So this is the way how we create 0, 1, 3, 2, 4, 5, 7, 6. So here 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, sorry, it's 0 and here 1. So this will be for A and this is for B and C. Now we need to put the values, or rather the ones which is present in the cell. So this is cell number 0, 1, 2, 3, 4, 5, 6 and 7. So from here we see cell number 1 and 2 is given 1. Cell number 1 and 2 is given 1. Next, cell number 4 and 7 are 1. So 4 and 7 are 1. Now from this we can see that with the help of the K-map it's not possible for us to simplify the Boolean expression. And moreover, all of them are present in diagonal form, which represents that normally the condition where the ones are present in the K-map diagonal form, naturally the response, or rather the Boolean expression, will be in XOR form. But still, in order to experiment that, we will be writing those individual expression of the ones such that we can able to specify that the expression will be after obtaining the K-map will give me a XOR. So what will I write down here? We are using for PE, even parity. Now the expressions will be, what do we get here? This is your A, B bar, C. This is your first one. A means for SOP we consider this as normal and 0 will be complement. So for this one, what do we see here? That this will give me A bar, B, A, B bar, C. So this will give me A, this will give me B bar and this will give me C bar. Next will be for A, B bar, C. That means this will give me this one. So this will give me A bar since it's 0, then B bar and C. Next is A, that means number 1, A for 1A, then both of them are 1, so B and C. And finally for this one will give me, since A is 0, so A bar, then for B1 will be B, then C bar. Now we will be taking B bar common here. I will get A, C bar plus A bar, C. Plus if I consider here B common, AC plus A bar, C bar. So we already know that this will give me a XOR expression. So B bar is A XOR C. And this is what B, this is the form of XNOR. That means AC, this will be, sorry, this will give me B, A, XNOR C. That means the XOR gate again will be complemented by using a NOT gate to make me XNOR. So this can also be written in the form B bar A XOR C plus B A XOR C complement. That means XNOR is represented in the form of XOR and complement. Now if I take this particular expression as X, this will give me what? B bar X plus BX bar. And this expression, it will be in the form of XOR, since we already know if I need to find out XOR between two bits, then that expression gives me A C bar plus A bar C. So this will give me a XOR expression. Same thing we have received here. So now if I say this is the expression given me, that means it's a XOR expression. So now we can write down here B XOR X, and X is nothing but A XOR. So it's B XOR A XOR C. So this is the expression, final expression for even parity. And the same thing, if you want to represent in the form of logic diagram, how will you represent that? If you have A, B, C, so you have lines here. first thing will be what? A XOR C. So you consider here, if I consider here as B XOR A XOR C, we'll have B XOR A. This is B XOR A, and that is XORed with C. So this is the logic diagram or logic circuit diagram for my even parity bit. Same thing we can do it for the odd parity also, but the only difference will be just the complement of my even parity. Okay, now we will be looking into a next video that how will we design for the odd parity, and then after finding out that, we'll be getting out the checker to find out whether the response is giving me correct response or not.